Hello everyone. Here we were studying about the correlation receiver, in which we will require detector or a modulator, and at the transmission side we will require a decoder. So we have seen baseband digital signal is a signal which we can transmit without any modulations. So we can say the baseband signal can either come from a source like computer or any digital communication system. You can take delta modulation, adaptive delta modulation, ADM, any. So here we can say when we are doing the transmission and reception of a digital signal without considering the effect of noise on this signal. So here we can say noise is an important parameter because we can consider it while designing any communication system, because as we are supposed to reduce the distortion, we are supposed to improve signal to noise ratio, so that digital communications will be good. So here we can say when we are supposed to design the baseband receiver, our aim is to minimize its error probability. So here we can see electrical noise and interference which are produced by variety of sources within a receiver as well as outside the receiver. So we can say the sources of noise can any, like atmospheric noise, switching, intermodulation noise. We can say that noise can be a thermal noise. So with proper precautions we can minimize, or we are supposed to eliminate the effect of noise, and we are supposed to reduce the interference entering the receiver except thermal noise. So here we are saying noise is random in nature. So you can say thermal noise also will be expressed as random in nature. Then we have seen if we are supposed to consider the binary encoded signal, how we are taking that is nothing but we are taking received signal, that will be the signal which we have sent plus additive white Gaussian noise. So we can take R of t equal to S of t plus Wt, where Wt is nothing but additive Gaussian white noise with zero mean. So these concepts we have already seen. Now what we are supposed to see? We are supposed to see optimum matched filter and their mathematical parameters, like how to derive its probability of error, how to derive its impulse response. So if we are using the optimum filter, and at that time the noise is nothing but additive white Gaussian noise, we can say that as a match filter. If you want, you can see here the diagram for the match filter. When we will get the received signal, we are giving that to the match filter. Here we are supposed to sample this, and here you will get that output received. We can call that as a observation vector. So here we can say when we are using the optimum filter with zero mean, we can say that as a match filter. And what we have seen in the optimum filter, if we are supposed to use the optimum filter, at that time the integrate and dump circuit will emphasize a signal output in comparison with the noise voltage. So here we can say error probability is only dependent on energy upon the noise. So we can say here error probability is dependent on EB by N naught ratio. But here we are supposed to use optimum filter to improve SNR. To improve SNR, here we are supposed to reduce intersymbol interference. So when we are using the optimum filter, at that time binary signal is transmitted, it get corrupted by noise, which we are calling as a Gaussian noise. So we will get R of t received signal equal to signal which we have sent S of t plus noise N of t. This is the Gaussian noise. So we can say if the received signal is filtered by using the match filter, you can see here we are using the match filter. If we are filtering received signal and sampled, you can see here we are sampling at time t equal to capital T as shown in diagram. So here you will get the output. How you will get? If we are taking output as Y of t, input we are taking as a X of t, received signal. So here you will get output Y of t, that is nothing but which we will get after sampling, which comes from the match filter. So you will get y of t equal to s naught t plus n naught t. So here we can say s naught t will be produced by s of t and n naught t will be produced by n of t. So here you will get the sample output that we can take y of t equal to s naught of t plus n naught of t. So here we can say if we are using here decision circuit, the decision threshold we will get as lambda equal to s naught 1 of t upon s naught 2 of t upon 2. So here you will get the decision threshold that equal to s naught 1 plus s naught 2 upon 2. So here we are supposed to find its probability. How you will get its probability? Because here we are supposed to reduce the error probability. So we can say in order to find the error probability at the receiver side, we can consider one signal is get transmitted out of 2. So here you will get the probability of error like this. The meaning we will see in the next class. Thank you.